Hello, in this lecture we'll answer on two questions. In the first question we find out the area of this big circle, and in the second question we find out the area of this rectangle ABCD using two different methods. So we start with the first question. In the drawing we have two circles that are tangent to each other at this point C. In addition, we know that this is line segment AC, it is equal to 6 units length. This is line segment CV, that is equal to 9 units in its length. And this is tangent DE, that is tangent to this small circle at this point B. And tangent DE also tangent to this circle at this point. So we define the point of tendency of tangent DE with this big circle. This point is point M. Point B is considered as a common extreme point in relation to this big circle. Again, point B is considered as a common extreme point in relation to this big circle. So from point B, that is the common extreme point, we have here tangent BM to the big circle. The point of tendency of tangent BM with this big circle is point M. In addition, from the same common extreme point B, we have this straight line that cuts the circle at 2 points. The big circle at 2 points. Point B cuts the big circle at 2 points. Point C and point A. In this way, we created here chord CA. So here we can implement rule 10. So let's pick rule 10. According to rule 10 is true in any circle. So in any circle, if AB is any chord in the circle and PT is a tangent to this circle at point T. So from this common extreme point A, we have tangent PT, and also we have here chord AB. So in this drawing, the following equation is true, that PT square equals to PA times PB. Again, PT square equals to PA times PB. So whenever you have a common extreme point, and from a common extreme point you will draw a straight line that cuts the circle at 2 points. In this way you create a chord. In this case it is chord AB. And from the same common extreme point B, you will draw a tangent to a circle. Then in the drawing, the following equation will be true, that PT square equals to PA times PB. Again, PT square equals to PA times PB. So we can actually implement rule 10 in our drawing. Why? Because if we focus on this common extreme point B, from this common extreme point B, we have tangent BM that is tangent to this big circle at point M. And in addition, we also have here, if we draw a straight line, this straight line from the same common extreme point B, we create here chord CA. So all the requirements of rule 10 are satisfied, and therefore we can implement here rule 10. According to rule 10, we get that BM square equals to BC times BA. Again, BM square equals to BC times BA. So I'll write it down. So from the common extreme point B, according to rule 10, the following equation is true. That BM square equals to BC times BA. Repeat again. If we focus on the common extreme point B, according to rule 10, the following equation is true, that BM square equals to BC times BA. Again, BM square equals to BC times BA. BM is the missing tangent, so we leave it as it is, so it is BM square. That is equal to BC. BC is 9 times BA. BA in total, it is equal to 16 plus 9, that is 25. So in total, we found out that according to rule 10, BM square equals to 9 times 25. Here we take a root out of this equation, and we get that BM is equal to the square root of 9, that is 3, times the square root of 25, that is 5. So in total, BM equals to 3 times 5, that is 15. So if we found out that the length of tangent BM is equal to 15 units. So here, tangent BM equals to 15 units in its length. In the next step, we will do a construction. That is to say, from this point of tendency between the two circles, that is actually point C, we will draw a straight line that touches tangent DE. From this point C, we draw a straight line that touches tangent DE. We define the touching point of the common tangent with tangent DE. This point is point N. Again, CN is actually a common tangent because CN is tangent to this big circle point C, and tangent CN is also a tangent to the small circle at the same point C. So CN is a common tangent that belongs to both circles. In the next step, we'll join point C and M together by a straight line. And we'll focus on this point N. From this common external point N. Again, point N is a common external point in relation to both circles. Why? Because point N is not located inside those circles, nor on those circles. It is located outside the circles, and therefore point N is considered as a common external point. So from this common external point N, we have two tangents to this small circle, tangent NB and tangent NC. And according to rule 2, they are equal to each other. That is to say, NB equals to NC. So I repeat quickly rule 2. According to rule 2, the lengths of two tangents from a common external point to a circle are equal. In the drawing, we have a circle, and this is the common external point P. From this common external point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule 2, they are equal to each other. That is to say, PA equals to PB. So as I mentioned, we can implement rule 2 in our drawing. Why? Because in our drawing, from this common external point N, we have two tangents to this small circle, tangent NB and tangent NC. And according to rule 2, they are equal to each other. That is to say, NB equals to NC. In the next step, I'll copy triangle C and B. In the new page, and we'll analyze this triangle C and B. Actually, this is triangle CNB that are covered from the original drawing according to rule 2. Side CN equals to side NB. And we have the rule that says that in front of equal sides in the triangle there are equal angles. In front of this side CN we have this is angle CBN, and in front of this side NB we have this angle. It is actually angle NCB. And according to the rule that I mentioned, in front of those two equal sides we have those two angles that, because of those two angles are located in front of those two equal sides, they must be also equal to each other in their sizes. So if the size of this angle is alpha, then the size of this angle must be also equal to alpha, because they must be equal to each other according to the rule that I mentioned. So in total we shall find out that angle CNB equals to alpha and angle CBN also equals to alpha. So actually this is angle CNB, this is angle CNB, that is equal to alpha. This is actually angle NCB equals to alpha, angle NCB equals to alpha, and the second angle that is equal to alpha, this is angle CBN. So angle CBN, this is angle CBN, that is also equals to alpha. In the next step, we'll continue to focus on this common example point N. From this common example point N, we have two tangents to the big circle, tangent NC and tangent NM, and according to rule 2 they are equal to each other. That is to say, CN equals to NM. So in the next step I'll copy triangle CMN in a new page, and we'll analyze this triangle CMN. So actually, this is triangle CMN that I copied from the original drawing. According to rule 2, side CN equals to side MN. And according to the rule that I mentioned, that in front of equal sides in the triangle there are equal angles. So in front of this side CN, we have this angle, this is actually angle CMN, and in front of this side MN, we have this angle, that is actually angle NCM. And because of the fact that those two angles are located in front of those two equal sides, they must be also equal to each other in their sizes. So if the size of this angle NCM is equal to beta, then the size of this angle CMN must be also equal to beta, because they must be equal to each other according to the rule that I mentioned. So in total we shall find out that angle MCN equals to beta and angle CMN also equals to beta. So here angle MCN equals to beta and angle CMN also equals to beta. Okay, so in the next step I'll copy triangle MCB, the big triangle MCB that consists of those two small triangles in a new page, and we'll analyze this big triangle, triangle MCB. So actually, this is triangle MCB that I copied from the original drawing. We know that all the angles in a triangle, the sum of the angles in a triangle is equal to 180 degrees. And especially this rule is true in this triangle, triangle CMB. So which angles we have in this triangle CMB? This is angle alpha, plus this is angle beta, plus this angle, that is angle beta plus alpha. In total, the sum of those three angles must be equal to 180 degrees according to the rule that I mentioned. Alpha plus alpha is 2 alpha, and beta plus beta is 2 beta. So in total, we shall find out that 2 alpha plus 2 beta equals to 180 degrees. Here we divide this equation by 2 and finding that alpha plus beta equals to 180 degrees over 2 is 90 degrees. So we shall find out that alpha plus beta is equal to 90 degrees. So actually, angle BCN, this is angle MCB, this is the big angle MCB equals to alpha plus beta. Again, angle MCB equals to alpha plus beta. And we know that angle MCB is equal to 90 degrees, because alpha plus beta equals to 90 degrees. So angle MCB is a right angle. Angle MCB is a right angle. So this is angle MCB, that is a right angle. We know that AB is a straight line. According to what is given us the question, AB is a straight line. So if we focus on the left side of the straight line AB at point C, here the sum of the angles must be equal to 180 degrees according to rule 3 that states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the left side of AB at point C? We have this is a right angle plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. That is to say, angle MCA is a right angle. In the next step, we join points A and M together by a straight line. And we focus on the big circle. Inside this big circle, we have peripheral angle ACM, and this is peripheral angle ACM. The size of this peripheral angle ACM is 90 degrees according to rule 3. So angle ACM is a right angle, and peripheral angle ACM subtend on chord AM. Again, peripheral angle ACM subtend on chord AM. Okay. Now we can implement here rule 5. I'll repeat quickly rule 5. According to rule 5, any peripheral angle that is equal to 90 degrees must subtend on the diameter of the circle. So in the drawing we have a circle, and this is peripheral angle MAN. Peripheral angle MAN is a right angle, it is equal to 90 degrees in its size, and therefore peripheral angle MAN must subtend on the diameter of this circle. That is to say, MN is the diameter of the circle. So we have here peripheral angle that is equal to 90 degrees in its size, and therefore it must subtend on the diameter of the circle. That is to say, MN is the diameter of the circle. So any peripheral angle that is equal to 90 degrees in its size, it must subtend on the diameter of the circle. So we can definitely implement rule 5 in our drawing. Why? Because in our drawing, in the big circle, we have peripheral angle ACM, that is a right angle, and therefore peripheral angle ACM, that is a right angle, must subtend on the diameter of this circle. And because of the fact that peripheral angle ACM subtends on chord AM must be the diameter of the circle. Again, according to rule 5, chord AM must be the diameter of the circle, because peripheral angle ACM that is equal to 90 degrees in size is subtend on chord AM. And any peripheral angle that is equal to 90 degrees in size must subtend on the diameter of the circle. And therefore, chord AM is the diameter of the circle. So we found out that according to rule 5, chord AM is the diameter of the circle. And we know that the center of the circle must be located on the diameter of the circle. Again, the center of the circle must be located on the diameter of the circle. And therefore, the center of this big circle must be located somewhere on AM, that is the diameter of the circle. So, we define this point as point O, and point O is the diameter of is the center of the circle. Point O is the center of the circle. You can see here that point O is indeed located on the diameter AM of this circle. So we know that point O is the center of the circle. Point M is the point of the circle itself, therefore OM is the radius of this circle. We define the radius of this circle OM as R. So the radius OM is equal to R. The radius OM of this big circle is drawn to point M, that is the point of tendency or tangent DE with this big circle. And whenever you have a radius that is drawn to the point of tendency, then tangent DE will be perpendicular to the radius MO. If DE is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. In the next step, I'll copy the right triangle A and B in a new page, and we'll implement the Pythagoras theorem on this right triangle A and B. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse AB in total equals to 16 plus 9, that is 25, and MB equals to 15 units according to rule 10. AM is the missing side. Here by PT is the version for Pythagoras theorem. So actually, this is triangle A and B that are coined from the original drawing. According to the Pythagoras theorem, in this right triangle A and B, AB squared, it is the square of the hypotenuse, equals to AM squared plus MB squared. So I write it down. AB squared, it is the square of the hypotenuse, is equal to AM squared plus MB squared. MB equals to 15 units in its length according to rule 10. AB is 25, therefore AB squared is 25 squared, that is 625, and it is equal to AM squared. AM is the missing side, so we leave it as it is, plus MB squared. MB is 15, therefore MB squared is 15 squared, that is 225. So in total we should find out that 625 equals to AM squared plus 225. Here we subtract 225 from this equation, and we get that 625 minus 225 is 400. So 400 equals to AM squared. Here we take out from this equation, and we get that AM equals to the square root of 400, this is 20. So AM equals to 20 units in its length. Therefore AM, this is side AM, that is equals to 20 units in its length. We only found that chord AM is the diameter of the circle. AM is the diameter of this big circle. So the diameter AM equals to 20 units in its length. Therefore, the radius must be equal to half of it. So the radius R must be equal to the diameter AM over 2. AM is 20, so the radius must be equal to 20 over 2, that is 10. So we found out that the radius R of the big circle is equal to 10 units in its length. Our mission is to find out the area of this big circle. Actually, the area of any circle is equal to pi times the radius of the circle squared. Repeat again. The area of any circle is equal to pi times the radius of the circle squared. And therefore the area of our big circle must be equal to pi times the radius of the circle squared. The radius of the circle is 10, therefore the radius squared is 10 squared. So in total, the area of our circle, the area of the big circle, must be equal to pi times 10 squared. 10 squared is 100, so in total this expression equals to 100 pi. 100 pi is equal to 314.159 square units. And that is the answer to the question. Repeat again. Actually found out that the area that we are looking for in this question, that is the area of this big circle, it is equal to either 100 pi square units, or in terms of numbers, it is equal to 314.159 square units. We finished with the first question. In the next step, I will present you the second question, and we'll solve the second question in two different methods. Our mission in the second question is to find out the area of this rectangle ABCD. So in the drawing we have rectangle ABCD, and we have also this semicircle. We know that this is line segment AM, that is equal to 5 units in its length. Again, our mission is to find out the area of this rectangle ABCD. We start with the first method. So first of all, because of the fact that ABCD is a rectangle, all those four angles inside rectangle ABCD must be equal to 90 degrees in their sides. Now all right angles. So actually, this is a right angle. This is also a right angle. This is a right angle. And finally, this is also a right angle. In the next step, we'll define the center of this semicircle. This point is point O. We'll define the radius of this semicircle as x. So point O is the center of the semicircle. Point A is the point of the semicircle itself. Therefore, OA is the radius of the semicircle that is equal to x units in its length according to our definition. In the next step, we'll define the point of tendency of tangent DC with this semicircle. This point is point E. So in the next step, we join points E and O together by a straight line. Point O is the center of the semicircle. Point E is the point of the semicircle itself. Therefore, OE is the radius of this semicircle that is equal to x units in its length according to our definition. So OE equals to x units in its length. Because of the fact that the radius OE that is equal to x, the radius OE is drawn to point E, that is the point of tendency of tangent DC with this semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent DC will be perpendicular to the radius EO. If DC is perpendicular to EO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. By doing this construction, we actually create a deal. Quadrilateral DEOA. Inside this quadrilateral DEOA, we have 1, 2, 3 right angles. This is a right angle because all the angles inside right angle ABCD are right angles. So inside quadrilateral OEDA, we have 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this 4th missing angle, in total they must be equal to 360 degrees according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this 4th missing angle must be equal to 90 degrees in its size. So inside the small quadrilateral DEOA, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be its right angle if not a square. So we relate to this quadrilateral DEOA as right angle because it has 4 right angles. So actually quadrilateral DEOA is right angle according to rule 5. But we also know that the opposite sides of a left angle are equal to each other. So a left angle DEOA, side OE must be equal to the opposite side DA. But OE is x, therefore DA must be also equal to x units in its length. In the next step, we define this line segment OB as A. And we define this line segment MB as B. In the next step, we join points O and M together by a straight line. What is the definition of line segment OM? Line segment OM starts from point O, that is the center of the semicircle, and then at point M, that is the point on the semicircle itself. So this is exactly the definition of a radius. Therefore, OM is the radius of this semicircle that is equal to x. OM equals to x. In the next step, I'll copy this right triangle OMB in a new page, and we'll implement the Pythagoras theorem on this right triangle OMB. Here by PT is the relation for Pythagoras theorem. So finally, this is the right triangle OMB that I copied from the original drawing according to the Pythagoras theorem. In this right triangle OMB, OM squared, that is the square they produce, equals to MB squared plus BO squared. So write it down. OM squared, that is the square of the hypotenuse, is equal to MB squared plus OB squared. OM is x, therefore OM squared is x squared, and it is equal to OB squared. OB is a, therefore OB squared is a squared, plus MB squared. MB is b, therefore MB squared is b squared. So in total, according to equation 1, we actually found out that x squared equals to a squared plus b squared. In the next step, I'll copy the right big triangle A and B in a new page, and we will implement the Pythagoras theorem on this big right triangle A and B. AM equals to 5, the hypotenuse AM of the right triangle AB equals to 5 units in its length, according to what is given us in the question. What is the length of side AB of triangle A and B? AB in total equals to x plus A. AB equals to x plus A. So actually, this is the right triangle A and B that I copied from the original drawing according to the Pythagoras theorem, and this right triangle A and B. MA squared, that is the square of the hypotenuse, equals to MB squared plus BA squared. So I'll write it down. This will be equation 4. According to equation 2, MA squared, the square of the hypotenuse, is equal to mb squared plus ab squared. MA is 5, therefore MA squared is 5 squared, that is 25, and it is equal to MB squared. MB is x plus a, therefore MB squared is x plus a squared plus AB. Actually, AB is x plus a, therefore AB squared is x plus a squared plus MB squared. MB is b, therefore MB squared is b squared. So in total, according to the Pythagoras theorem, it is right angle A and B. 25 equals to x plus a squared plus b squared. So this is equation 2. So according to equation 2, 25 equals to x plus a squared. X plus a squared equals to x squared plus a squared plus 2 times x times a plus b squared. So in this side of equation 2, we have the expression a squared plus b squared. According to equation 2, according to equation 1, we already found out that a squared plus b squared equals to x squared. Therefore, we can substitute a squared plus b squared in this equation 2 by x squared from this equation, equation 1. We'll do it now and we get that 25 equals to a squared plus b squared is x squared plus x squared plus 2xa. So in total, according to equation 2, we actually found out that 25 equals to x squared plus x squared is 2x squared plus 2xa. So in total, according to equation 2, we actually found out that 25 equals to 2x squared plus 2xa. Here we divide this equation 2 by 2, and you get that 25 over 2 is 12.5, and it is equal to 2x squared over 2 is x squared plus 2xa over 2 is xa. So in total, according to equation 2, we actually found out that 12.5 equals to x squared plus xa. So 12.5 equals to, here we take out x as a common factor from those two expressions. So x will take it out as a common factor. So inside the brackets we left with x plus a. So in total, according to equation 2, we actually found out that x times x plus a equals to 12.5. Our mission is to find out the area of this rectangle ABCD. Actually, the area of any rectangle equals to the length of the rectangle times the width. Repeat again, the area of any rectangle equals to the length of the rectangle times the width. And therefore, the area of rectangle ABCD must be equal to the length of the rectangle ABC times the width. The length of this rectangle ABCD is equal to AB times the width. The width of this rectangle ABCD is DA. So in total, we shall find out that the area of rectangle ABCD equals to the length AB times the width DA. AB in total equals to x plus a. dA in total equals to x. So we shall find out that the area of rectangle ABCD equals to x plus a times x. But according to equation 2, x plus a times x is 12.5. So we substitute x plus a times x by 12.5. So in total we shall find out that the area of rectangle ABCD equals to 12.5 square units. And that is the answer to the question. I'll repeat it again. We actually found out that the area of this rectangle ABCD is equal to 12.5 square units. So we finish with the first method. In the next step, I will present to you how to find out the area of this rectangle ABCD according to the second method. So, first of all, because of the fact that ABCD is a rectangle, all of its four angles, those four angles are all right angles. So, see, this is a right angle. This is also a right angle. This is a right angle. And finally, this is also a right angle. We define the center of this semicircle. This point is point O. We define the radius of this semicircle as x, exactly as we did in the first method. So here point O is the center of the semicircle, point A is the point of the semicircle itself, therefore OA is the radius of this semicircle that is equal to x units according to our definition. We have already found out in the first method that AD equals to x, so I will not repeat on the same explanation. AD equals to x according to the first method. In the next step, we will define this point as point N. We will define the line segment OB as A. And we'll join points M and N together by a straight line. By doing this construction, we can get here peripheral angle NMA. This is peripheral angle NMA. And because of the fact that peripheral angle NMA subtend on AN, and AN is the diameter of the semicircle, peripheral angle NMA must be equal to 90 degrees in its size, according to rule 7 that says that any peripheral angle that subtend on the diameter of the circle or a semicircle must be equal to 90 degrees in its size. So repeat quickly on rule 7. According to rule 7, if a peripheral angle subtend on the diameter of the circle, then it is equal to 90 degrees. So in the drawing, we have a circle, and this is peripheral angle ACB that subtend on AB. That is the diameter of the circle, and because of the fact that peripheral angle ACB subtend on the diameter of the circle, it must be equal to 90 degrees in its size. This peripheral ACB equals to 90 degrees in its size according to this rule, rule 7. So we can implement rule 7 in our drawing. It's already mentioned. Because of the fact that peripheral angle AMN subtend on AN, that is the diameter of this semicircle, it must be equal to 90 degrees in its size according to rule 7. So this is peripheral angle AMN that subtend on the diameter of the semicircle, and therefore it is equal to 90 degrees in size according to rule 7. In the next step, we define this angle as angle alpha, and we focus on the right triangle AMN. In the right triangle AMN, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in a triangle. In the next step, we'll focus on this triangle, the right triangle A and B. This right triangle A and B, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. Exactly because of the same reason, because of the fact that 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in a triangle. In the next step, I'll copy the right triangle AMN and this right triangle A and B in a new page, and we'll prove that those two right triangles are similar to each other according to angle similarity rule. So actually, those are the two right triangles A and B and A and N that I copied from the original drawing. So those two right triangles are similar to each other. First of all, those two angles are both equal to 90 degrees, and therefore they are equal to each other. So actually, this is angle MBA. In the right triangle A and B, and it is equal to this angle, that is actually angle AMN. In the right triangle AMN, they are both equal to 90 degrees, and therefore they are equal to each other. In addition, this is actually angle A, that is a common angle that belongs to both triangles. So we can write out that angle A equals to itself as a common angle that belongs to both triangles. So if you relate to angle A as it belongs to the right triangle A and B, it will be angle MAB. And angle A equals to itself. So if you relate to angle A as it belongs to the right triangle AMN, it will be defined as angle MAN. So this equation means that angle alpha equals to itself. It just angle A or angle alpha equals to itself. You just call to angle alpha two different names. Angle alpha equals to itself. It's a common angle that belongs to both angles. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually this is angle A and B in the right triangle A and B, and it is equal to this angle. This is actually angle M and A in the right triangle A and M. They are both equal to 90 degrees minus alpha, therefore they are equal to each other. So in total we found out that all the triangles of this right triangle A and B are correspondingly equal to all the triangles of this right triangle A and M. Therefore those two right triangles are similar to each other according to angle similarity rule. So write it down. So the right triangle A and B, this is the right triangle A and B. That is similar, this is the sign of similar to the right triangle A and N, this right triangle A and N, according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive, but first of all, here it is given as the question that AM equals to 5 units in its length. AM equals to 5. According to our definition, actually AB in total equals to x plus A. AB equals to x plus A. AM. AM is the diameter of the semicircle. The radius of this semicircle is x, and therefore the diameter must be twice as big as the radius. The radius is x, therefore the diameter must be equal to 2x. So the diameter or AN of this semicircle equals to 2x units in its length. AN equals to 2x is the diameter of the semicircle. So because of the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AM of this right triangle A and B over side AN of this right triangle A and N is equal to side AB of this right triangle A and B over side AM of this right triangle AMN. So repeat again. From the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. That side AM of the right triangle A and B over side AN of the right triangle AMN equals to side AB of the right triangle A and B over side AM of the right triangle AMN. It is given as the question that AM equals to 5 units in its length over AN. I just right now explain to you that AN is the diameter of the semicircle that is equal to 2x, and here AB is x plus A, so I mentioned before, AB is x plus A, here AB, in total this is x plus A, over AM. AM is 5, so in total we found out that according to equation 1, 5 over 2x equals to x plus A over 5. Here we cross multiply this equation 1, and we get that 5 times 5 is 25 equals to 2x times x plus A. Here we divide this equation 1 by 2. And again, according to this equation 1, 25 over 2 is 12.5, and it is equal to 2x over 2 is x times x plus a. So in total, we actually found out that according to equation 1, x times x plus a equals to 12.5. Our mission is to find out the area of this semicircle, the area of this rectangle ABCD. Okay, our mission is to find out the area of this rectangle ABCD. Actually, the area of any rectangle equals to the length of the rectangle times the width. But again, the area of any rectangle equals to the length of the rectangle times the width. And therefore, the area of rectangle ABCD must be equal to the length of the rectangle ABC times the width of the rectangle ABCD. And the length of this rectangle ABCD is AB. The length is AB times the width. The width of this rectangle ABCD is AD. So in total, we shall find out that the area of rectangle ABCD equals to the length AB times the width AD. AB in total equals to x plus A. AB equals to x plus A times AD. AD equals to x. So in total, we shall find out that the area of rectangle ABCD equals to x plus A times x. Again, the area of rectangle ABCD equals to x plus A times x. But according to equation 1, x plus A times x is 12.5. So we substitute x plus A times x here by 12.5. So actually, in both methods, we found out that the area of rectangle ABCD is equal to 12.5 square units. Repeat again. In both methods, we found out that the area of this rectangle ABCD is equal to 12.5 square units. So in the next step, I will summarize the lecture. We'll start with the first question, of course. Our mission in the first question is to find out the area of this big circle. So in the drawing, we have those two circles that touch each other at this point C. In addition, we have a tangent DE that is tangent to this small circle at point B, and it is tangent to this big circle at point M. In addition, we know that this is line segment CV that is equal to 9 units in its length, and this is line segment AC that is equal to 16 units in its length. Again, our mission is to find out the area of this big circle. Okay. First of all, we define the point of tendency of tangent DE with this big circle, this point as point M. Point B is an external point in relation to this big circle. So from this common external point B, we have tangent BM to this big circle that is tangent to this big circle as point M. In addition, from the same common external point B, if we do this straight line, it will cut the big circle at 2 points, point C and point A. In this way we create chord CA. So all the requirements of rule 10 are satisfied, and therefore we can implement here rule 10. According to rule 10, the following equation is true. That BM squared equals to BC times BA. Again, BM squared equals to BC times BA. So repeat again, if you focus on the common standpoint point A and point B, if you focus on this common standpoint point B, according to rule 10, the following equation is true. That BM squared equals to BC times BA. Again, BM squared equals to BC times BA. BM is the missing tangent, so we leave it as it is. BM squared equals to BC. BC is 9 times BA. BA in total equals to 9 plus 16, that is 25. Repeat again. BC is 9 and BA is 25. So in total we shall find out that BM squared equals to 9 times 25. Here we took a root out of this equation and found out that BM equals to the square root of 9, that is 3, times square root of 25, that is 5. So in total BM equals to 3 times 5, that is 15. We shall find out that the length of this tangent BM is 15 units. Okay, in the next step we did a construction, that is to say, from the point of tendency of those two circles, that is to say from point C, we draw the common tangent that belongs to both circles until it touches tangent DE, and we define the touching point of the common tangent on DE. This point is point N. Again, CN is a common tangent that belongs to both circles. Suppose CN is tangent to the small circle, and CN also is tangent to the big circle. And the point of tendency in both cases is at point C. So CN is a common tangent that belongs to both circles. Again, we define the touching point of tangent CN with DE. This point is point N. So here we focus on this common standpoint point N. From this common standpoint point N, we have two tangents to the circle, tangent N to the small circle, tangent NC and tangent NB. And according to rule 2, they are equal to each other. That is to say, NC equals to NB. In the next step, we join point C and M together by third time. Then we copy triangle CNB in a new page, and we analyze this triangle CNB. Actually, this is triangle CNB that I copied from the original drawing. According to rule 2, CN equals to NB. And according to the rule that in front of equal sides in the triangle, there are equal angles. So, in front of this side CN, we have this is angle CBN. In front of this angle, in front of this side NB, we have this angle BCN. And because of the fact that those two angles are located in front of those two equal sides, they must be also equal to each other in their sizes. So if the size of this angle is alpha, then the size of this angle must be also equal to alpha, because they are equal to each other according to the rule that I mentioned. So in total, we shall find out that angle NCB equals to alpha, and angle NBC also equals to alpha. This is angle NCB that is equal to alpha, and angle CBN also equals to alpha. We'll continue to focus on this common standpoint point N. From this common standpoint point N, we have two tangents to the big circle, tangent NC and tangent NM. And according to rule 2, they are equal to each other. That is to say, NC equals to NM. In the next step, I copy this right triangle MCN. This triangle, it is not right triangle. I copy this triangle CNM in a new page, and I write this triangle CNM. Actually, this is triangle CNM that I copied from the original drawing. According to rule 2, CN equals to NM. According to the rule that states that in front of equal sides in the triangle there are equal angles, we get that in front of this side CN we have this angle, in front of this side MN we have this angle. And because of the fact that those two angles are located in front of those two equal sides, they must be also equal to each other in their sizes. So if the size of this angle is beta, then the size of this angle must be also equal to beta, because they must be equal to each other according to the rule that I mentioned. So in total, we actually found out that angle NCM equals to beta, and angle NMC also equals to beta. So actually, this is angle MCM that is equal to beta, and angle NMC also equals to beta. In the next step, I copy the big triangle MCB in a new page, and analyze this big triangle MCB. Actually, this is triangle MCB that I copied from the original drawing. This is angle alpha, this is angle beta, and angle MCB. This is angle MCB, that in total it is equal to alpha plus beta. Angle MCB equals to alpha plus beta. We know that the sum of the angles in any triangle is equal to 180 degrees, and especially the sum of the angles in this triangle MCB equals to 180 degrees. So which angles we have in this triangle MCB? We have this is angle alpha plus this is angle beta plus this is angle that is beta plus alpha. In total, they must be equal to 180 degrees. Again, alpha plus beta plus alpha. In total, they must be equal to 180 degrees according to the rule that I mentioned. In this side of the equation, we have alpha plus alpha, that is 2 alpha, beta plus beta is 2 beta. So in total, 2 alpha plus 2 beta equals to 180 degrees. We divided this equation by 2 and finally found out that alpha plus beta equals to 180 degrees over 2 is 90 degrees. So alpha plus beta, this is again alpha plus beta, that is equal to 90 degrees in its size. So actually, angle MCB is equal to alpha plus beta, and alpha plus beta, it is a right angle. That is to say, angle MCB is a right angle. Angle MCB is a right angle. It is given as the question that AB is a straight line. So if we focus on the left side of this straight line AB at point C, here the sum of the angles must be equal to 180 degrees according to rule 3 that states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the left side of AB at point C? We have this angle that is the right angle plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So I should have found out that angle ACM is a right angle. In the next step, we join points A and M together by a straight line and focus on the big circle. Inside this big circle, we have peripheral angle ACM. This is peripheral angle ACM, that is a right angle. And because of the fact that peripheral angle ACM is a right angle, according to rule 5, any peripheral angle that is equal to 90 degrees in its size must subtend on the diameter of the circle. And because of the fact that angle ACM is a right angle, it must subtend on the diameter of the circle. Angle ACM subtend on AM, and therefore AM must be the diameter of the circle. Repeat again, according to rule 5, chord AM must be the diameter of the circle. And because of the fact that the center of the circle must be located on the diameter of the circle. Again, the center of the circle must be located on the diameter of the circle. That is to say, the center of this big circle must be located on AM. So here, this is the center of this circle that we define as point O. Point O is definitely located on AM, that is the diameter of this circle. Point O is the center of the circle, point M is the point of the circle itself, therefore OM is the radius of this big circle. We define the radius of the big circle as R. Because of the fact that the radius OM that is equal to R, the radius OM is drawn to point M, that is the point of tendency of tangent DE with this big circle. And whenever we have a radius that is drawn to the point of tendency, then tangent DE will be perpendicular to the radius MO. If DE is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to rule 1. In the next step, I copied the right triangle A and B in a new page, and we implemented the Pythagoras theorem on this right triangle A and B. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares from the perpendiculars. The hypotenuse AB in total equals to 16 plus 9, that is 25. A and B equals to 15 units in itself according to rule 10. So actually, this is the right triangle A and B that are coming from the original drawing. According to the Pythagoras theorem, in this right triangle A and B, AB squared, that is the square of the hypotenuse, must be equal to AM squared plus MB squared. Again, AB squared equals to AM squared plus MB squared. AB is 25, therefore AB squared is 25 squared, that is 625. And it is equal to AM squared. AM is the missing side, so we leave it as it is, plus BM squared. BM is 15, therefore BM squared is 15 squared, that is 225. So in total we actually found out that 625 equals to AM squared plus 225. Here we subtracted 225 from this equation, and finally found out that 625 times 225 is 400, so 400 equals to AM squared. We took a root out of this equation and finally found out that AM equals to the square root of 400, that is 20. So actually found out that the diameter AM is equal to 20 units. If the diameter AM of the big circle is 20, it means that the radius must be equal to half of it. That is to say, the radius half of the big circle must be equal to the diameter AM over 2. AM is 20, so 20 over 2 is the radius of the big circle, and 20 over 2 is 10. So the radius of the big circle is equal to 10 units in its length. Our mission is to find out the area of this big circle. Actually, the area of any circle equals to pi times the radius of the circle squared. And therefore, the area of our circle must be equal to pi times the radius of our big circle squared. The radius of the big circle is 10, and therefore the radius squared is 10 squared. So in total, the area of the big circle must be equal to pi times 10 squared. 10 squared is 100, so in total this expression equals to 100 pi. 100 pi is 314.159. So in total, if you found out the area that we're looking for this question, the area of this big circle equals to either 100 pi square units. So in terms of numbers, the area of the big circle equals to 314.159 square units. We finished with the first method. In the next step, I presented to you how to find out the area of this big circle according to the second method. Actually, we finished with the first question, and in the next step, I present to you the second question of this lecture. We solved the second question in two different methods. Our mission in the second question is to find out the area of this rectangle ABCD. So in the drawing, we have a rectangle ABCD, and also this semicircle. This is line segment AM, that is equal to 5 units in its length. Again, our mission is to find out the area of this rectangle ABCD. Because of the fact that ABCD is a rectangle, all of its 4 angles are right angles. We define the center of this semicircle, this point is point O. We define the radius of this semicircle as x. Point O is the center of the semicircle, point A is the point of the semicircle itself, therefore OA is the radius of this semicircle, that is equal to x units in its length according to our definition. We define the point of tendency DC with this semicircle, this point is point E. In the next step, we join points O and E together by a straight line. Point O is the center of the semicircle, point E is the point of the semicircle itself, therefore OE is the radius of this semicircle, that is equal to x. Because of the fact that the radius OE, that is equal to x, the radius OE of this semicircle is drawn to point E, that is the point of tendency of tangent DC with this semicircle. And whenever your radius that is drawn to the point of tendency, then tangent DC will be perpendicular to the radius EO. If this is perpendicular to EO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. When doing this construction, you can do the small quadrilateral DEOA. Inside this small quadrilateral DEOA, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the side of this fourth missing angle, in total it must be equal to 360 degrees according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in its side. So inside quadrilateral DEOA, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be a rectangle, if not a square. So we have to polygon of DEOA is a rectangle because it has 4 rectangles. But we also know that the opposite sides of a rectangle are equal to each other. So a rectangle DEOA, side EO must be equal to the opposite side DA. But EO is x, therefore DA must be also equal to x units in its length. In the next step, we join points O and M together by side line. Point O is the center of the semicircle, point M is the point of the semicircle itself, therefore OM is the radius of this semicircle that is equal to x units in its length. We define this line segment OB as A, and we define this line segment BM as B. In the next step, I copy the right triangle OMB in a new page and implemented the Pythagoras theorem on this right triangle OMB. This is the right triangle OMB that I copied from the original drawing. According to the Pythagoras theorem, this right triangle OMB, OM square, that is the square of the hypotenuse, equals to MB square plus BO square. OM is x, therefore OM square is x square, and it is equals to OB square. OB is a, therefore OB square is a square, plus MB square. MB is b, therefore MB square is b square. So in total, according to equation 1, we shall find out that x square equals to a square plus b square. In the next step, I copied this right triangle A and B in a new page and implemented the Pythagoras theorem, and this right triangle A and B. This is the right triangle A and B that I copied from the original drawing. AB in total equals to x plus A. AM equals to 5 units in its length according to all the segments in the question, and A and B equals to B according to all definition. This right triangle A and B according to the Pythagoras theorem. AM square equals to MB square plus BA square. AM is 5, therefore AM square is 5 squared, that is 25, and it is equals to MB square. MB is B, therefore MB square is B square, plus AB square. AB is x plus A, therefore AB square is x plus A square. So in total, according to equation 2, I shall find out that 25 equals to x plus A square plus B square. So 25 equals to x plus A square. X plus A square equals to x square plus A square plus 2 times A times x plus B square we have here. So here, in this side of the equation 2, we have the expression a square plus b square. But according to equation 1, a square plus b square equals to x square. Therefore, we can substitute a square plus b square in this equation 2 by x square for this equation 1. We did it, and we shall find out that 25 equals to a square plus b square is x square, and we have x square again, plus 2xa. So in total, according to equation 2, we shall find out that 25 equals to x square plus x square plus 2xa. X square plus x square is 2x square. So in total, we shall find out that 25 equals to 2x square plus 2xa. And again, according to equation 2, we shall find out that 25 equals to 2x square plus 2xa. Here we divided this equation 2 by 2. We finally found out that 25 over 2 is 12.5. And it is equal to 2x square over 2 is x square, and 2xa over 2 is xa. So in total, we shall find out that according to equation 2, 12.5 equals to x square plus xa. So 12.5 equals to, here we took out x as a common factor from those two expressions, so inside the brackets we left with x plus a. So in total, according to equation 2, we should find out that 12.5 equals to x times x plus a. Our mission is to find out the area of this rectangle ABCD. Read again, our mission is to find out the rectangle ABCD. Actually, the area of an rectangle equals to the length of the rectangle times the width. And therefore, the area of rectangle ABCD must be equal to the length of the rectangle ABCD times the length, times the width. The length of this rectangle ABCD is AB, and the width is DA. And again, the length is AB, and the width is DA. So therefore, the area of rectangle ABCD must be equal to AB times DA. AB is x plus A, and DA is x. So in total, the area of rectangle ABCD must be equal to x plus A times x. But x plus a times x, according to equation 2, x plus a times x is 12.5. So we can substitute x plus a times x by 12.5. We did it, and actually found out that in total the area of rectangle ABCD is equal to 12.5 square meters. We finished with the first method. In the next step, I presented to you how to find out the area of this rectangle ABCD according to the second method. Again, because of the fact that all the triangle ABCD is a rectangle, all those four angles are right angles. We defined the center of this semicircle, this point is point O. In the first one, we defined the radius of this semicircle as x. So OA is the radius of the semicircle, that is x. DA equals to x according to the first method. we define this line segment OB as A, and we define this point as N, and we join points N and M together by straight line. By doing this construction, we can do peripheral angle AMN. Peripheral angle AMN subtend on AN, that is the diameter of the semicircle, and any peripheral angle that subtend on the diameter of the semicircle or circle must be equal to 90 degrees inside. Therefore, peripheral angle AMN must be equal to 90 degrees according to rule 7. Okay. In the next step, we define this angle as angle alpha. So in the right angle AMN, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first vice angle must be equal to 90 degrees minus alpha. Likewise, in the right angle AMB, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first vice angle must be equal to 90 degrees minus alpha. In the next step, I copy the right angle AMN and AMB in the new page, and we prove that those two right angles are similar to each other according to angle similarity rule. So actually, those are the two right angles, AMN and AMB, that are correct from the original drawing. But those two right angles are similar to each other. First of all, those two angles are both equal to 90 degrees, and therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. And finally, this is angle A, that is a common angle that belongs to both angles, so we can write down that angle A equals to itself as a common angle that belongs to both angles. So we actually found out that all the three angles on the right angle A and B are approximately equal to all the three angles of the right angle AMN. And therefore those two right angles are similar to each other according to angle similarity rule. And from the fact that those two right angles are similar to each other, we derive that the following relationship exists between their sides. We derive that AM over AN equals to AB over AM. AM is 5, AN is 2x, AB is x plus A, and AM is 5. Because multiply the equation 1, and find out that 25 equals to 2x times x plus A. We divided the equation 1 by 2, and finally found out that 25 over 2 is 12.5, 2x over 2 is x, so in total this expression equals to x plus x times x plus a. So in total, according to equation 1, we actually found out that 12.5 equals to x times x plus a. Our mission is to find out the area of this rectangle A, B, C, D. The area of any rectangle equals to the length of the rectangle times the width. And therefore the area of rectangle ABCD must be equal to the length of the rectangle ABCD times the width. The length of this rectangle ABCD is AB, and the width is AD. AB times AD. AB is x plus A, and AD is x. So in total, the area of the ABCD equals to x plus A times x. But according to equation 1, x plus A times x is 12.5. Therefore, we can substitute x plus A times x by 12.5. We did it, and we actually found out in total the area of the rectangle ABCD equals to 12.5 square units. So in both methods, we found out that the area of this rectangle ABCD is equal to 12.5 square units. Okay, thank you very much.